Hello, and welcome to the Restful Stories. Settle in as we prepare to leave the familiar behind and venture out into the silent, star-strewn immensity that surrounds our world. It is a realm of unimaginable scales and breathtaking phenomena, a place where the laws of physics paint a canvas of profound and often surprising beauty. If the thought of journeys to these distant shores of knowledge excites you, be sure to subscribe to the channel so you'll always be notified when we release new stories. The universe, as we will discover, is not merely a visual spectacle of distant, glittering lights. It is a full sensory experience, engaging us in the most unexpected of ways and revealing truths that challenge our very perception of reality. It is a story written in the language of gravity and light, of time and space, a narrative that unfolds across billions of years and even greater distances. To begin to read its pages, we must open our minds not just to what can be seen, but to what can be imagined. Our journey begins not with a sight, but with a scent, a fragrance that permeates the very heart of our own galaxy. If you could somehow unhelmet your senses in the vast dust cloud at the center of the Milky Way, you would be greeted by an aroma that is surprisingly familiar, a combination that evokes thoughts of tropical drinks and summer desserts. The core of our galaxy, a region known as Sagittarius B2, smells distinctly of rum and raspberries. This cosmic perfume is not a flight of fancy, but the result of chemistry on a galactic scale. Astronomers, using radio telescopes to analyze the chemical signatures of deep space, detected vast quantities of a molecule called ethyl formate. Here on Earth, this is the very compound that gives raspberries their sweet, fruity flavor and is a key component in the complex aroma of rum. It floats through the interstellar medium, a ghostly reminder that the building blocks of experiences we hold dear, taste and smell, are not exclusive to our world, but are woven into the fabric of the cosmos itself. The sheer scale of this fragrant cloud is difficult to comprehend, a testament to the universe's capacity for creating complexity in the most desolate of places. This chemical richness extends far beyond simple flavors. In another corner of the distant universe, surrounding a quasar, one of the most luminous and energetic objects known, lies a reservoir of another, even more fundamental substance. Astronomers have discovered a colossal cloud of water vapor, the largest and most distant body of water ever detected. It contains an amount of water that beggars belief, a staggering 140 trillion times the total volume of all the oceans on our home planet. This celestial ocean, however, is not a liquid sea, but a vast, gaseous nebula spanning hundreds of light years and existing in a universe that was still in its infancy more than 12 billion years ago. Its presence tells us that water, the essential ingredient for life as we know it, has been abundant in the cosmos almost since the very beginning, hinting at the potential for life-bearing worlds far beyond our own imagining. The existence of such immense structures of gas and dust underscores the nature of the vacuum that separates them. Space is not truly empty, but its near-perfect vacuum creates conditions utterly alien to our terrestrial experience, giving rise to physical phenomena that seem to defy common sense. Consider what happens when two pieces of metal meet in this environment. Here on Earth, a thin, invisible layer of oxidized material forms on their surfaces almost instantly, a barrier created by their interaction with the air. This layer prevents the atoms of one piece from directly touching the atoms of the other. But in the vacuum of space, this protective layer does not form. If two pieces of the same type of metal, perfectly clean and smooth, are brought into contact, they will do something remarkable. They will fuse together, becoming a single, solid piece. This process, known as cold welding, occurs because the atoms in each piece of metal cannot distinguish their own lattice structure from that of the other piece. With no intervening air or oxidation, they bond together as if they were always one. This principle is not a mere curiosity. It is a critical engineering challenge for building satellites and spacecraft, where a simple, unintended contact could lead to a permanent and potentially catastrophic fusion of components. This strange, empty world physics has shaped the very celestial bodies we observe. Let us turn our gaze closer to home, to our constant companion in the night sky, the moon. We picture it as a perfect sphere, a flawless silver orb. But this is an illusion of distance. In reality, the moon is subtly misshapen, more akin to a lemon than a perfect ball. It possesses flattened poles and two distinct bulges around its equator, one on the side facing us and another on the side facing away. This unusual shape is a relic of its dramatic formation and its complex relationship with Earth. In the distant past, when the moon was still a molten sphere of rock, the powerful gravitational pull of our own planet created immense tidal forces, stretching the young moon into this oblong shape. Over eons, as the moon cooled and solidified, this distorted form was frozen in place, a permanent scar of its gravitational dance with Earth. This profound gravitational influence did not just sculpt the moon's physical form, it dictated its very motion, choreographing a celestial ballet that continues to this day. The same tidal forces that warped the moon's shape also acted as a brake on its rotation. Over billions of years, Earth's gravity tugged at the moon, slowing its spin until its rotational period precisely matched its orbital period around our planet. This phenomenon, known as tidal locking, is why we only ever see one face of the moon. It completes a single rotation on its axis in the exact same amount of time it takes to complete one orbit of the Earth, keeping its far side perpetually hidden from our view. The so-called dark side of the moon is a misnomer. It receives just as much sunlight as the near side, but it remains a hemisphere of mystery, forever turned away from a direct terrestrial gaze. While our moon is locked in this synchronous rhythm, other worlds in our solar system spin to far more alien beats. Consider Venus, our planetary neighbor, a world of crushing pressure and searing heat. Here, the relationship between a day and a year is inverted in a way that confounds our earthly intuition. A single day on Venus, the time it takes for the planet to complete one full rotation on its axis, is 243 Earth days long. In stark contrast, its journey around the Sun, its year, takes only 225 Earth days. A Venusian day is therefore longer than a Venusian year. Imagine a world where the sun rises in the west, crawls with agonizing slowness across the sky for months, and sets in the east, all before the planet has even finished a single trip around its star. This bizarre state of affairs is likely the result of a cataclysmic impact in Venus's distant past, a collision so powerful it slowed the planet's rotation to a near standstill, and may have even reversed its direction. Such planetary eccentricities, however, are but minor details in the grand architecture of our solar system, an architecture utterly dominated by the star at its center. The sun, our source of light and life, is an object of almost inconceivable mass. It accounts for an astonishing 99.86% of the total mass of the entire solar system. Everything else, all 8 planets, from the gas giants Jupiter and Saturn to our own rocky world, along with every moon, asteroid, and comet, is little more than a cosmic rounding error, a fleeting remnant of the primordial nebula from which the sun itself was born. Its immense gravitational field dictates the orbits of all celestial bodies in its vicinity, a constant and overwhelming presence that holds our world and all others in its unwavering grasp. This dominance in mass does not, however, translate to a dominance in space. The distances between worlds are so vast that they defy easy visualization. Yet, a curious thought experiment reveals the scale of this emptiness. If one were to gather all the other planets in our solar system, Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune, they could all fit side by side in the gulf of space that separates the Earth from its own moon. This is only possible, however, when the moon is at its apogee, its farthest point from Earth, a distance of approximately 407,000 kilometers, or about 253,000 miles. The combined diameters of all 7 other planets add up to just less than this immense distance, a startling illustration that the heavens are composed mostly of void. Within this void, however, exist objects of such extreme density that they challenge our understanding of matter itself. In the aftermath of a supernova, the explosive death of a massive star, the core can collapse under its own gravity crushing protons and electrons together to form a city-sized sphere made almost entirely of neutrons. This object, a neutron star, is one of the densest phenomena in the known universe. The sheer weight of this exotic matter is staggering. A single teaspoonful, a volume of just 5 milliliters, of neutron star material would have a mass of over 1 trillion kilograms, which is more than 1.1 trillion US tons. This tiny amount of matter would weigh more than all the mountains on Earth combined. A concentration of mass so profound that it bends both space and light. From the impossibly dense to the ethereally thin, the cosmos presents a tapestry of endless variety. Even a simple, familiar event like a sunset is transformed on another world. On Mars, an observer would witness a spectacle quite different from the fiery reds and oranges of an earthly dusk. As the distant, smaller sun dips below the Martian horizon, the sky around it would glow with an eerie, captivating blue light. This phenomenon is a result of the fine Martian dust that permeates its thin atmosphere. While the dust scatters red light across the sky, making the daytime sky a pale pinkish red, it has the opposite effect at sunrise and sunset. The particles scatter red light forward, away from an observer looking toward the sun, while allowing blue light to penetrate more directly along the line of sight. It is a hauntingly beautiful and deeply alien inversion of the familiar. A final reminder that even the light that illuminates other worlds tells a different story. That alien light falls upon a landscape of equally alien proportions, a world where the forces of geology have operated on a scale unmatched on Earth. This is the domain of Olympus Mons, a volcano so immense that it dwarfs any feature on our own planet. Rising from the Tharsis volcanic plateau of Mars, this colossal shield volcano stands at an altitude of nearly 22 kilometers, or about 13.6 miles, making it approximately 3 times the height of Mount Everest, our own world's tallest peak, measured from sea level. Its base would cover an area comparable to the nation of France, a footprint so vast that if you were to stand at its edge, the summit would lie far beyond the horizon, its gentle slope indistinguishable from the curvature of the planet itself. The sheer scale of Olympus Mons is a direct consequence of the unique geological conditions of Mars. The red planet has a much lower surface gravity, only about 1/3 that of Earth's, allowing volcanic structures to grow taller before collapsing under their own weight. More crucially, Mars lacks the active plate tectonics that constantly reshape our own world. On Earth, the crust is fragmented into plates that drift over the molten mantle. This means that a volcanic hotspot will create a chain of smaller volcanoes as the crust moves over it, like the Hawaiian Islands. On Mars, the crust remained stationary. A single, massive hotspot was able to pour out lava in the same location for hundreds of millions of years, building a single, gigantic mountain layer by agonizing layer, an uninterrupted monument to a geologically quiet world. From this world of solid, gargantuan rock, we journey outward, past the asteroid belt, to the realm of the gas giants, where planetary substance takes on an entirely different meaning. Here, we find Saturn, the ringed jewel of the solar system, a world of majestic beauty and surprising levity. While it is the second largest planet, it is by far the least dense. In fact, Saturn is the only planet in our solar system with an average density less than that of water. Its density is approximately 0.7 grams per cubic centimeter, whereas liquid water on Earth has a density of 1 gram per cubic centimeter. This has given rise to the famous thought experiment. If one could find a bathtub large enough, Saturn would float. This is more than just a charming piece of trivia. It reveals the planet's fundamental composition. It is a world made not of heavy rock and metal, but primarily of the lightest elements in the universe, hydrogen and helium, which exist in gaseous and liquid metallic states deep within its interior. Saturn is a celestial puffball, a vast and airy sphere whose substance is spread so thinly across its enormous volume that it could bob like a cork in a cosmic ocean. Journeying further into the chilling depths of the outer solar system, we encounter the ice giants, Uranus and Neptune, twin worlds of deep blue hues and profound cold. Here, we find a curious paradox that defies simple logic. Uranus, the seventh planet from the Sun, is actually the coldest planet in the solar system, despite Neptune being the eighth and therefore much farther away. The cloud tops of Uranus can plummet to a staggering minus 224 degrees Celsius, which is minus 371 degrees Fahrenheit. This is colder than Neptune's already frigid average of minus 214 degrees Celsius, or minus 353 degrees Fahrenheit. This temperature anomaly points to a dramatic and violent history. The leading theory suggests that in the distant past, a protoplanet the size of Earth collided with Uranus. This cataclysmic impact could have knocked the planet onto its side, explaining its bizarre 98-degree axial tilt, and in the process caused it to expel most of the primordial heat trapped within its core. Uranus, in essence, was cracked open, venting its internal furnace into space billions of years ago. Neptune, by contrast, retains a significant internal heat source, radiating more than twice the energy it receives from the distant Sun, keeping its atmosphere surprisingly dynamic and slightly warmer than its closer neighbor. The vast distance that separates Neptune from the Sun also governs its sense of time, stretching its years into epic lengths that dwarf a human lifespan. The planet was first observed in the year 1846, a discovery that was a triumph of theoretical physics. Its existence and location had been predicted mathematically by observing gravitational wobbles in the orbit of Uranus. Since that moment in the mid-19th century, a period when great changes were sweeping across Earth, Neptune has been slowly, methodically tracing its enormous path around the Sun. It completed its very first full orbit since its discovery in the year 2011. A single Neptunian year lasts for approximately 165 Earth years. It is a time scale so grand that entire eras of human history can pass in the space of one of its seasons, a humbling reminder of the patient, deliberate pace of the cosmos. While the outer planets mark time in centuries, the inner worlds dance to a much stranger, faster rhythm. On Mercury, the planet closest to the Sun, the relationship between a day and a year is contorted into a state of extreme temporal distortion. Here, a single solar day, the time from one sunrise to the next, is twice as long as the planet's entire year. This is the result of a complex gravitational relationship known as a 3-to-2 spin-orbit resonance. For every 2 trips Mercury makes around the Sun, a journey of just 88 Earth days each, it rotates on its axis exactly 3 times. This intricate celestial waltz means that an observer on the surface would experience about 59 Earth days of scorching daylight, followed by an equal length of frigid night, all within a single, swift year. The Sun would appear to hang almost motionless in the sky, a searing, oversized orb in a world where a day feels like an eternity. But even the frozen darkness of Mercury's long night is a furnace compared to the coldest known location in the universe, a place that makes even the outer planets seem balmy. This is the Boomerang Nebula, located some 5,000 light-years away from Earth. Here, the temperature drops to just 1 degree Kelvin, which is minus 272 degrees Celsius, or minus 458 degrees Fahrenheit. This is colder than the faint afterglow of the Big Bang, the cosmic microwave background radiation that permeates all of space and sets a baseline temperature of about 2.7 Kelvin. The Boomerang Nebula achieves this incredible cold because it is a young planetary nebula, the expelled outer layers of a dying central star. This gas is being ejected outwards at a tremendous velocity, about 164 kilometers per second, or over 367,000 miles per hour. This rapid expansion forces the gas molecules apart, causing them to cool dramatically, much like the expanding refrigerant in an air conditioner. It is a cosmic refrigerator of unparalleled efficiency, creating the only natural environment found so far that is colder than the background temperature of the universe itself. From this point of ultimate cold, we turn our attention to an object of ultimate size. The Boomerang Nebula's star is dying, but other stars exist in a state of unimaginable magnitude. The largest known star is a red hypergiant named Uy Scuti. Its sheer scale is difficult to articulate. If Uy Scuti were to replace our Sun at the center of our solar system, its surface, or photosphere, would extend far beyond the orbit of Jupiter. It would completely engulf Mercury, Venus, Earth, Mars, the asteroid belt, and the largest of the gas giants. Our own world would not be orbiting this star. It would be vaporized deep within its tenuous outer layers. Its radius is estimated to be around 1,700 times that of our Sun, giving it a volume so immense that approximately 5 billion suns could fit inside it. This single star is a cosmic monster, a testament to the extremes of stellar evolution. And yet, for all its size, UY Scuti is just one of countless stars. The total number of stars in the observable universe is a figure that pushes the boundaries of human comprehension, a quantity best understood through comparison. It is now widely accepted by astronomers that there are more stars in the heavens than there are grains of sand on all the beaches and in all the deserts on Earth. While both numbers are estimates, the figures are revealing. Scientific calculations place the number of grains of sand at roughly 7.5 sextillion. The estimated number of stars in the observable universe, however, is closer to 1 septillion, a 1 followed by 24 zeros. This suggests there are at least 100 stars in the sky for every single grain of sand on our planet. A silent, glittering testament to the sheer fecundity of the cosmos. This stellar abundance leads to an even more profound realization. For a long time, we wondered if our solar system, with its family of planets, was a cosmic anomaly. But thanks to decades of painstaking observation and dedicated space missions, we now understand that planets are not the exception, but the rule. The current scientific consensus is that most, if not nearly all, stars are likely to have at least one planet orbiting them. The formation of planets appears to be a natural and common byproduct of the formation of stars. This means that for every one of those septillion stars, there is likely a world, or a system of worlds, in its gravitational embrace. The galaxy is not a collection of lonely suns, but a teeming metropolis of solar systems. And at the end of the lives of the most massive of these stars lies one of the most misunderstood phenomena in the universe: the black hole. The name itself conjures an image of perfect blackness, a cosmic void. Yet, ironically, the region surrounding a black hole can be one of the brightest places in the universe. This is because black holes are not completely black, as immense amounts of gas, dust, and even entire stars are drawn in by a black hole's inescapable gravity. The material does not fall directly in. Instead, it is whipped into a frenzy, forming a vast, flat, spinning structure called an accretion disk. The friction and intense gravitational and magnetic forces within this disk heat the matter to millions of degrees, causing it to glow with unimaginable brilliance across the entire electromagnetic spectrum, from radio waves to powerful X-rays. It is this intensely luminous disk, not the black hole itself, that astronomers observe, a blazing halo of light surrounding a point of perfect darkness, a final, brilliant scream from matter before it crosses the event horizon and vanishes from our universe forever. That point of perfect darkness, the event horizon, marks a boundary of no return, a concept that finds its most extreme expression in the very heart of our own galaxy. At the center of the Milky Way, just as in the centers of most large galaxies, lies an object of almost unbelievable mass and density, a supermassive black hole. Ours is named Sagittarius, a star, a designation that identifies it as a powerful radio source located within the constellation of Sagittarius. This is not a stellar mass black hole born from the collapse of a single giant star. Sagittarius, a star, is a true monster, possessing a mass equivalent to approximately 4.3 million of our suns, all condensed into a region of space smaller than the orbit of Mercury. For decades, its existence was inferred, a ghostly gravitational presence required to explain the frantic, high-speed orbits of the stars nearest the galactic center. Astronomers watched these stars whip around an unseen focal point at speeds of thousands of kilometers per second, their trajectories providing irrefutable proof of the immense mass hiding in the darkness. In the year 2019, this indirect evidence was finally supplemented by a direct image, not of Sagittarius, a star itself, but of the supermassive black hole at the heart of the galaxy, Messier 87, a feat of global scientific collaboration that made the invisible visible for the first time. Our galaxy, this vast, spinning disk of stars and gas that Sagittarius A star anchors, is just one of countless cosmic islands scattered across the observable universe. We classify these islands, these galaxies, based on their appearance, a system first developed by the pioneering astronomer Edwin Hubble in the early 20th century. This galactic taxonomy divides them into four main types. First are the spiral galaxies, like our own Milky Way and our neighbor Andromeda. These are characterized by a bright central bulge of older stars surrounded by a flat, rotating disk of gas, dust, and younger, bluer stars, all arranged in graceful, sweeping arms. Then there are the elliptical galaxies, which are more three-dimensional, appearing as giant, football-shaped conglomerations of older, redder stars, with very little gas or dust, and thus very little new star formation. Lenticular galaxies represent a sort of intermediate stage, possessing a central bulge and a disk, but lacking the distinct spiral arms of their more photogenic cousins. Finally, there are the irregular galaxies, a catch-all category for those that fit no neat classification, their shapes often chaotic and disrupted, likely the result of gravitational encounters or collisions with other galaxies. Each of these galactic forms tells a story of its formation, its history, and its interactions with its cosmic neighbors. The closest of these major neighbors to our own Milky Way is the Andromeda Galaxy, also known as Messier 31, a magnificent spiral, even larger than our own. It is visible to the naked eye as a faint, hazy smudge in the autumn sky of the northern hemisphere. It lies approximately 2.5 million light-years away, a distance so vast that the light we see from it tonight began its journey when our earliest human ancestors were first walking the plains of Africa. But this vast gulf is not static. It is shrinking. Andromeda is hurtling toward the Milky Way at a speed of about 110 kilometers per second, or nearly 250,000 miles per hour. This trajectory places our two galaxies on a collision course, destined to merge in a spectacular event that will reshape our local cosmic environment forever. This galactic collision is not an event to be feared in the immediate sense. It is scheduled to begin in about 4.5 billion years, roughly the same time that our sun will begin to swell into a red giant. When it happens, it will not be a cataclysm of crashing stars. The distances between individual stars are so immense that direct stellar collisions will be exceptionally rare. Instead, it will be a gravitational dance of breathtaking scale as the two galaxies pass through each other, their structures distorted and thrown into chaos by their mutual pull. Over hundreds of millions of years, they will merge, their stars intermingling to form a new, much larger galaxy, likely a giant elliptical galaxy, which some astronomers have already nicknamed Milkomeda. This grand cosmic event, however, is a mere spectacle within a much larger and far more mysterious cosmic arena. The galaxies, stars, planets, and all the visible matter that we can observe, from the smallest asteroid to the largest galactic supercluster, constitute only a tiny fraction of the universe's total mass and energy. The overwhelming majority of the cosmos is made of two enigmatic substances that we cannot see or directly detect: dark matter and dark energy. All the visible matter we know makes up only about 4 to 5% of the universe's total content. About 27% is thought to be dark matter, a mysterious substance that does not emit or interact with light, but whose gravitational effects are observable in the rotation of galaxies and the bending of light from distant objects. The remaining 68% is even more bizarre: dark energy, a hypothetical form of energy that permeates all of space and is believed to be responsible for the accelerating expansion of the universe. We are, in a very real sense, living in a universe dominated by forces we do not yet understand. Our familiar world of matter and light being just the luminous foam on a deep, dark, cosmic ocean. The existence of dark energy is implied by one of the most profound discoveries of modern cosmology: the fact that the universe is not only expanding, but that this expansion is speeding up. For most of the 20th century, It was believed that the expansion of the universe, initiated by the Big Bang, should be slowing down due to the gravitational attraction of all the matter within it. However, in the late 1990s, observations of distant supernovae revealed the opposite. These cosmic beacons showed that distant galaxies were moving away from us faster than they should be, indicating that some unknown force was pushing space apart, counteracting gravity on the largest scales. This acceleration means that the ultimate fate of the universe may be a big rip, where the expansion becomes so rapid that it will eventually tear apart galaxies, stars, planets, and even the very atoms of which we are made. This expanding space carries with it the light from distant objects, a fact that has profound implications for how we view the cosmos. When we look at a distant star or galaxy, we are not seeing it as it is now, but as it was when the light we are observing first began its journey towards us. Light travels at a finite speed, approximately 300,000 kilometers per second, or about 186,000 miles per second. This means that observing distant objects is equivalent to looking back in time. The light from Andromeda shows us that galaxy as it was 2.5 million years ago. Light from more distant galaxies can show us a universe that was billions of years younger, still in the process of forming its first major structures. The most distant light we can detect, the cosmic microwave background, is a snapshot of the universe when it was only 380,000 years old. Astronomy is, in this sense, a form of time travel, allowing us to piece together the history of the cosmos by observing its ancient light. But not all the light in our night sky is ancient or distant. Some of it is remarkably close, a product of our own species' burgeoning presence in space. After the sun and the moon, the third brightest object that can be seen in the sky is the International Space Station, or ISS. This football field-sized orbiting laboratory, mankind's permanent outpost in space, circles the Earth at an altitude of about 400 kilometers, or 250 miles. Its large solar arrays are highly reflective, catching the sunlight and making it appear as a brilliant, fast-moving star gliding silently across the dawn or dusk sky. For observers on the ground, a pass of the ISS is a bright and tangible connection to the human endeavor in space. A reminder that we are no longer confined to the surface of our world. The cost of maintaining this human presence in such a hostile environment is immense, exemplified by the single most complex piece of equipment an astronaut wears: the spacesuit. A modern spacesuit, known as an extravehicular mobility unit, or EMU, is not merely a set of clothing. It is, in effect, a personal, human-shaped spacecraft. It must provide a pressurized atmosphere, breathable air, temperature regulation to protect against the extreme heat of direct sunlight and the extreme cold of shadow, radiation shielding, and micrometeoroid protection. It is a self-contained life support system, and the engineering and materials required to build one are extraordinary. Consequently, the cost of a single space suit can be upwards of $12 million. It is a price tag that reflects the incredible challenge of keeping a fragile human being alive in the lethal vacuum of space. Those astronauts who are fortunate enough to live and work aboard the ISS experience a reality where the fundamental rhythms of life are dramatically altered. The station orbits the Earth at a blistering speed of about 28,000 kilometers per hour, or about 17,500 miles per hour. This means it completes a full circle of our planet in approximately 90 minutes. As a result of this rapid orbit, the crew of the ISS witness about 16 sunrises and 16 sunsets every 24 hours. Their days and nights are not governed by the slow rotation of the Earth beneath them, but by the relentless clockwork of their own orbit. They live in a state of perpetual, fleeting dawns and dusks, a constant and beautiful reminder of their unique and privileged perspective on our world. From this vantage point, high above the distorting effects of the air, the stars do not twinkle. That familiar, gentle shimmering of starlight we see from the ground is not a property of the stars themselves, but an optical illusion created by our own planet's atmosphere. As the focused point of light from a distant star enters our atmosphere, it must pass through turbulent layers of air of varying temperatures and densities. These layers act like lenses, constantly bending and redirecting the light path in tiny, random ways. To our eyes, this rapid and chaotic refraction of the starlight causes it to appear as if it is twinkling. For an astronaut in orbit, or for a telescope in space, the stars are steady, unwavering points of pure, clear light shining against the perfect blackness of the void. That unwavering, pure starlight illuminates worlds of incredible violence and extreme conditions, none more so than our neighboring planet, Venus. Often called Earth's sister planet due to its similar size and mass, Venus is anything but hospitable. It holds the dubious distinction of being the hottest planet in our solar system, a title it claims despite being nearly twice as far from the Sun as Mercury. Its surface temperatures are a uniform and hellish 462 degrees Celsius, or 864 degrees Fahrenheit, hot enough to melt lead. This extreme heat is not a result of its proximity to the Sun, but of its atmosphere, which has created a runaway greenhouse effect on a planetary scale. The Venusian atmosphere is incredibly dense, exerting a surface pressure more than 90 times that of Earth's, equivalent to the pressure found nearly a kilometer, or over half a mile, deep in our oceans. This atmosphere is composed almost entirely of carbon dioxide, a potent greenhouse gas. Sunlight filters through the clouds and heats the planet's surface, but the thick carbon dioxide blanket traps this heat, preventing it from radiating back into space. Over billions of years, this process has intensified, baking the planet into the infernal, superheated world we see today. A cautionary tale written in the language of atmospheric physics. The clouds that shroud this planetary furnace are equally forbidding, composed not of water vapor, but of corrosive droplets of sulfuric acid. This means that on Venus, it does not rain water, but a shower of highly concentrated acid. However, the surface of the planet is so intensely hot that this acid rain never actually reaches the ground. It evaporates in the dense, superheated lower atmosphere, a phenomenon known as virga, creating a perpetual cycle of acid formation and evaporation in the upper cloud layers. Any probe or lander sent to explore this world must contend not only with crushing pressures and searing temperatures, but also with an atmosphere that is actively trying to dissolve it. This is a world where the very air is an agent of destruction. Moving outward from this acid-bathed inferno, we return to the majestic realm of Saturn, a planet whose serene beauty belies the extreme and violent nature of its own atmosphere. Here, at the planet's North Pole, swirls a weather system unlike any other in the solar system, a gigantic, hexagonal-shaped storm. This remarkable geometric feature, known as the Saturn hexagon, is a persistent cloud pattern, a six-sided jet stream that is wider than two Earths combined. The winds within this jet stream roar at speeds exceeding 480 kilometers per hour, or 300 miles per hour, confining the storm and maintaining its astonishingly straight, angular sides. Scientists believe the hexagon is a type of stationary wave, a feature rooted deep within the planet's atmosphere, its shape dictated by the specific properties of the winds at that particular latitude. It is a stunning example of the spontaneous emergence of order from chaos, a natural geometric marvel sculpted by the complex fluid dynamics of a gas giant's atmosphere, a storm that has likely raged for centuries, if not millennia. The famous rings that encircle Saturn, the source of its celestial fame, are themselves a study in contrasts, at once vast in their expanse and incredibly delicate in their structure. From a distance, they appear as solid, cohesive bands of material, but they are, in fact, composed of countless individual particles of ice and rock, ranging in size from tiny dust grains to chunks as large as mountains. These rings stretch out to a diameter of some 282,000 kilometers, or 175,000 miles. Yet they are, for the most part, astonishingly thin. In most places, their vertical thickness is only a few hundred meters at most, perhaps as little as 10 meters, or about 30 feet in some regions. This extreme thinness is a result of the constant collisions between the ring particles. Any particle that strays into an inclined orbit will quickly collide with others and be forced back into the main, flat plane of the rings. If you were to create a scale model of Saturn 1 meter, or about 3 feet, wide, Its rings would be thinner than a single sheet of paper, a celestial structure of immense breadth and almost non-existent depth. This phenomenon of orbiting debris is not exclusive to planets. Even the smaller bodies of the solar system can host their own miniature satellite systems. We have discovered that asteroids, the rocky remnants from the formation of the solar system, can possess their own moons. The first confirmed asteroid moon was discovered in 1990. 3. A tiny body named Dactyl found orbiting the larger asteroid Ida. Since then, we have found dozens of such systems. Even more surprisingly, in 2014, astronomers discovered that an asteroid named Chariklo possesses its own set of two dense and narrow rings, just like a miniature Saturn. This discovery challenged our understanding of how ring systems form and persist, as it was thought that only a massive body with a strong gravitational field, like a giant planet, could sustain such a feature. It seems that the complex gravitational dynamics that create rings can operate on a much smaller scale than we ever imagined. While these asteroids follow their steady orbits, other celestial bodies visit our inner solar system on much more dramatic and fleeting schedules. Among the most famous of these visitors is Halley's Comet, a celestial wanderer composed of ice, dust, and rock. It is a short-period comet, meaning it completes its vast, elliptical orbit around the Sun in a period of less than 200 years. Halley's Comet is visible from Earth approximately every 75 to 76 years, a regularity that has allowed it to be observed and recorded by astronomers around the world for more than 2 millennia, with the earliest known sighting dating back to at least 240 BCE. Its last appearance in our skies was in 1986, a pass that was met with an international flotilla of spacecraft sent to study it up close. Its next predicted return will be in the year 2061. For humanity, the periodic return of Halley's Comet serves as a kind of celestial clock, a reliable marker against which we can measure the passage of our own history and generations, a constant and predictable presence in an ever-changing sky. Beyond the orbits of these comets, in the vastness of interstellar and intergalactic space, the universe is filled with a faint, almost imperceptible glow, a form of radiation that is not associated with any particular star or galaxy. This is the cosmic microwave background, or CMB, and it is nothing less than the afterglow of the Big Bang itself. It is the oldest light in the universe, a fossil relic from a time when the entire cosmos was a hot, dense, opaque plasma. About 380,000 years after the Big Bang, the universe had cooled enough for atoms to form, and the light that had been trapped within the plasma was finally set free to travel unimpeded through space. Over the subsequent 13.8 billion years, the expansion of the universe has stretched the wavelengths of this primordial light, red shifting it from visible light into the microwave portion of the electromagnetic spectrum. Today, it appears as a faint background hum of radiation, a nearly uniform temperature of 2.7 Kelvin, coming from every direction in the sky. It is the echo of creation, a baby picture of the universe that provides one of the strongest pieces of evidence for the Big Bang Theory. While the CMB represents the gentle, fading embers of the universe's birth, other cosmic events unleash bursts of energy of almost unimaginable violence. Among the most powerful of these are gamma-ray bursts, or GRBs, which are intense, fleeting flashes of the highest energy form of light. These bursts can be unleashed during the formation of a black hole, either from the collapse of a hypergiant star or the merger of two neutron stars. In the few seconds that a gamma-ray burst lasts, it can release more energy than our sun will produce in its entire 10 billion-year lifetime. If such an event were to occur within our own galaxy and be pointed directly at Earth, it could have catastrophic consequences, potentially stripping away our atmosphere and triggering a mass extinction event. Thankfully, these events are incredibly rare and typically occur in distant galaxies, making them safe to observe from afar. They are the most luminous electromagnetic events known to occur in the universe, temporary beacons that can outshine their entire host galaxy. A brief, terrifying glimpse into the cosmos's most extreme energetic processes. For eons, our solar system was a closed environment, its contents believed to be exclusively its own. But in 2017, that perception was shattered by the arrival of an object from another star. It was a small, fast-moving body detected by a telescope in Hawaii, and its trajectory was not a closed orbit around our sun, but a hyperbolic path, meaning it was just passing through and would eventually leave our solar system forever. It was the first confirmed interstellar object ever observed. Its official name is 1I 2017 U1, but it is more famously known by its nickname, Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. The object was also peculiar in its shape. Observations of its changing brightness suggested it was highly elongated, perhaps a bizarre cigar-shaped object, unlike any asteroid or comet seen in our solar system. Its strange characteristics have led to a great deal of scientific debate and speculation, a fleeting visit from a true alien that has left us with more questions than answers. Our own solar system, however, holds its own brand of exotic phenomena, including a form of precipitation that sounds like it was drawn from a myth or a fairy tale. Deep within the crushing atmospheres of the ice giants, Uranus and Neptune, conditions are so extreme that it is theorized to rain diamonds. The immense pressure and high temperatures in the mantles of these planets, thousands of kilometers below the cloud tops, are thought to be capable of breaking down hydrocarbon compounds, like methane, which is abundant in their atmospheres. The carbon atoms are then squeezed together under pressures millions of times that of Earth's atmosphere, crystallizing to form solid diamonds. These newly formed diamonds would then, according to the theory, be denser than the surrounding material and would slowly sink or rain down through the deep layers of the planet's interiors, perhaps forming a solid diamond layer around their cores. It is a captivating image, a storm of jewels in the heart of a distant world, a process that transforms a simple gas into the hardest substance known. This cosmic alchemy, the transformation of simple elements into precious materials under extreme conditions, is not confined to the hearts of distant ice giants. It also occurs at the end of a star's life, leaving behind celestial objects that are, quite literally, cosmic jewels. Astronomers have discovered a star, a white dwarf designated BPM 37093, that is in essence a planet-sized diamond. Located about 50 light-years from Earth in the constellation Centaurus, this star has been nicknamed Lucy, a whimsical tribute to the Beatles' song Lucy in the Sky with Diamonds. A white dwarf is the collapsed core of a sun-like star that has exhausted its nuclear fuel. It is an incredibly dense object, composed mostly of carbon and oxygen, compressed into a sphere about the size of the Earth. Over billions of years, as this white dwarf cools, the intense pressure can cause the carbon within it to crystallize, a process identical to how diamonds form deep within our own planet, but on an astronomical scale. The result is a single, colossal diamond, estimated to be 10 billion trillion carats. Lucy is a testament to the fact that the universe can produce wonders that far exceed the scope of any earthly treasure. A star transformed into a flawless crystal, floating in the silent darkness of space. Our own celestial neighborhood is also a place of constant, albeit much slower, transformation. Our relationship with our own moon, for instance, is not static. The moon is gradually, almost imperceptibly, drifting away from the Earth. This slow retreat is a consequence of the same tidal forces that have locked the moon's rotation to its orbit. The Earth's gravity creates tidal bulges on the moon. And similarly, the moon's gravity pulls on Earth's oceans, creating our familiar ocean tides. Because the Earth rotates much faster than the moon orbits, the tidal bulge of our oceans is dragged slightly ahead of the moon's position in the sky. This leading bulge of water exerts a tiny gravitational tug on the moon, pulling it forward in its orbit and causing it to accelerate slightly. As it speeds up, it spirals outward into a higher orbit. The effect is minuscule, but measurable. Laser-ranging experiments, which bounce beams of light off reflectors left on the lunar surface by the Apollo astronauts, have confirmed that the moon is moving away from us at a rate of about 3.8 centimeters, or roughly 1.5 inches per year. This is approximately the same speed at which a human fingernail grows. In the distant past, the moon was much closer, appearing larger in the sky, and in the far future, it will be a smaller, more distant companion. This ever-changing distance also influences how we perceive the moon's brightness. A full moon, for instance, is significantly more luminous than a half moon, but the relationship is not linear as one might expect. A full moon is not merely twice as bright as a half moon. It is, in fact, about 9 to 10 times brighter. This disproportionate increase in brightness is due to a phenomenon known as the opposition surge. When the moon is full, the sun is directly behind us from our perspective on Earth, illuminating the lunar surface straight on. This means that there are no shadows being cast by the rocks, craters, and dust on the moon's surface from our point of view. Every feature is fully lit, and all the tiny shadows that would otherwise darken the landscape are hidden directly behind the objects casting them. This lack of shadows causes a dramatic surge in the amount of light reflected directly back at us, making the full moon appear exceptionally brilliant. In contrast, during a half-moon phase, the sunlight is coming from the side, casting long, deep shadows that cover a significant portion of the visible surface, drastically reducing its overall brightness. The Earth itself, the platform from which we observe these celestial phenomena, is also not the perfect sphere it often appears to be in diagrams. Our planet is technically an oblate spheroid, meaning it is slightly flattened at the poles and bulges out at the equator. This shape is a result of its rotation. The centrifugal force generated as the Earth spins on its axis is strongest at the equator, causing the planet's equatorial regions to bulge outwards. The diameter of the Earth from pole to pole is approximately 12,714 kilometers, or about 7,900 miles, while its diameter at the equator is about 12,756 kilometers, or about 7,926 miles. The difference is subtle, only about 42 kilometers, or 26 miles, but it is significant. This equatorial bulge means that the point on the Earth's surface farthest from the planet's center is not the summit of Mount Everest, but the peak of Mount Chimborazo, a volcano in Ecuador, which is located much closer to the equator. From this slightly flattened, bulging world, we look out into a galaxy that we now believe is teeming with other similar worlds. The search for exoplanets, planets orbiting other stars, has revealed that planetary systems are common, and a significant fraction of them may harbor worlds not unlike our own. Based on data from missions like the Kepler Space Telescope, astronomers now estimate that there could be as many as 10 billion potentially habitable Earth-like planets in our Milky Way galaxy alone. This staggering number is derived by calculating the fraction of stars that are similar to our Sun and then estimating how many of those are likely to have rocky planets orbiting within their habitable zone, the region where conditions might be right for liquid water to exist on the surface. While the presence of liquid water does not guarantee the existence of life, this calculation suggests that the raw materials and potential arenas for life are incredibly abundant throughout our galaxy, hinting at a cosmos far more vibrant and full of possibility than we ever dared to imagine. As we contemplate these billions of potential worlds, our own planet is constantly being dusted with the remnants of the cosmos. Every single day, the Earth is bombarded by a steady stream of interplanetary material. Most of this material is in the form of tiny dust particles, shed from comets, or liberated from asteroids by collisions. As the Earth moves through this cosmic dust, its gravity sweeps it up. The total amount of this material that falls to Earth is estimated to be about 14 tons, which is roughly 15 US tons every day. Most of these particles are microscopic and burn up harmlessly as shooting stars in our upper atmosphere. But the sheer volume of this celestial infall is a constant reminder that our planet is not an isolated system, but is actively accreting material from the wider solar system, a process that has been ongoing since its formation 4.5 billion years ago. The composition of this cosmic dust includes simple organic compounds, and some scientists believe this constant dusting may have played a role in delivering some of the key ingredients for life to the early Earth. The heavier, more precious elements found on Earth, however, have a far more violent and spectacular origin. Elements heavier than iron, such as gold and platinum, cannot be created in the cores of stars like our Sun through normal nuclear fusion. For a long time, their origin was a mystery, with supernovae being the leading but incomplete explanation. We now have strong evidence that these precious metals are forged in one of the most cataclysmic events the universe has to offer: the collision of two neutron stars. When two of these incredibly dense stellar remnants, locked in a decaying orbit, finally spiral into each other, the resulting explosion, called a kilonova, is so powerful that it creates a brief but intense environment where heavy elements can be rapidly synthesized through a process called R-process nucleosynthesis. The collision effectively seeds the surrounding space with newly minted gold, platinum, and other rare metals. The gold in a wedding ring, the platinum in a catalytic converter. These materials were not born on Earth, but were forged in the heart of a stellar collision that occurred billions of years ago, long before our solar system even existed. The material was then scattered across the galaxy, eventually becoming part of the nebula from which our own planet formed. We are, in a very literal sense, adorned with the wreckage of dead stars. The timescale over which such events play out is immense, often measured in galactic years. A galactic year also known as a cosmic year, is the time it takes for our solar system to complete one full orbit around the center of the Milky Way galaxy. Our solar system is traveling at an average speed of about 828,000 kilometers per hour, or 515,000 miles per hour. But the circumference of its orbit is so vast that one full revolution takes approximately 230 million Earth years. The last time our solar system was in its current position in the galaxy, the first dinosaurs were just beginning to appear on Earth. Since the Sun was born, it has completed only about 20 orbits around the galactic center. This grand, stately procession provides a sweeping perspective on cosmic time, a clock by which we can measure the evolution of not just our planet, but our entire stellar neighborhood. It was within this grand sweep of time that we first began to discover worlds beyond our own solar system. The very first exoplanets to be definitively confirmed were discovered in 1992, and they were found in a place no one expected, orbiting a pulsar. A pulsar is a rapidly spinning neutron star, the dense, collapsed core of a massive star that has gone supernova. This particular pulsar, designated PSR B1257+12, was found to have at least 2 planets orbiting it. Given the violent nature of a supernova, it is highly unlikely that these planets could have survived the explosion of the parent star. It is believed that they are second-generation planets, formed out of the debris disk that was left behind after the star's death. In a nod to the strange, ghostly nature of their existence around a stellar corpse, the planets were given the appropriately haunting names of Poltergeist and Phobiter. This discovery was a watershed moment, proving that planets could exist even in the most extreme and unlikely of environments. Within our own solar system, the diversity of worlds continues to astound. Among the more than 200 moons orbiting the planets, one stands out for its sheer, relentless geological activity. Jupiter's moon Io, the innermost of its 4 large Galilean moons, is the most volcanically active body in the solar system. Its surface is a chaotic, colorful landscape of yellows, reds, and blacks, constantly being repaved by the eruption of hundreds of volcanoes. Some of these eruptions spew plumes of sulfur and sulfur dioxide hundreds of kilometers high, far into space. This incredible volcanic activity is not driven by internal heat left over from its formation, but by the immense gravitational forces of Jupiter itself. Io is caught in a gravitational tug of war between the colossal planet and the other large moons, Europa and Ganymede. This constant squeezing and stretching of the moon's interior generates enormous frictional heat, keeping its subsurface molten and fueling its spectacular, ongoing eruptions. Io is a world perpetually tearing itself apart and being reborn in fire. The gravitational dance that tortures Io into a volcanic frenzy is a common theme throughout the solar system. But it can produce other, equally strange behaviors. far out in the cold, blue twilight of Neptune's domain, we find a moon that moves to a different beat, a large satellite that orbits its planet in the wrong direction. This is Triton, Neptune's largest moon, and it is unique among all the large moons in our solar system for its retrograde orbit. It travels around Neptune in a direction opposite to the planet's rotation. This orbital peculiarity is a telltale sign that Triton is not a native moon, not a body that formed from the same primordial disk of gas and dust as Neptune itself. Instead, Triton is almost certainly a captured object, a wanderer from the Kuiper Belt, that vast, icy debris field beyond the orbit of Neptune. Sometime in the distant past, Triton strayed too close to the giant planet and was ensnared by its gravity, its original independent orbit around the Sun, transformed into a captive, backward path around its new master. This violent capture would have had catastrophic consequences for Neptune's original satellite system, likely ejecting or destroying any moons that were already in place. Triton's retrograde orbit is also inherently unstable. The tidal forces between the two bodies are causing the moon to spiral, slowly but inexorably inward. In a few billion years, Triton will cross Neptune's Roche limit, the point at which the planet's tidal forces will be stronger than the moon's own gravity. It will be ripped apart, its icy remains forming a magnificent new ring system around Neptune that could rival or even surpass the splendor of Saturn's. From this celestial captive, we turn our gaze back to the heart of our solar system, to the star that orchestrates all of these motions. The Sun, while seemingly constant and eternal, is in fact a dynamic and active body, constantly shedding a portion of itself into space. This outflow of material is known as the solar wind, a continuous stream of charged particles, mostly protons and electrons, that emanates from the Sun's upper atmosphere, the corona. This wind flows outward at supersonic speeds, reaching velocities of up to 800 kilometers per second, or nearly 1.8 million miles per hour. While the individual particles are tiny, their collective mass is significant. Every second, the Sun loses about 1.5 million tons, or roughly 1.65 million US tons, of its mass to the solar wind. This stream of particles travels throughout the entire solar system, interacting with planetary magnetic fields to create auroras and shaping the tails of comets. It is a stellar breath that fills the interplanetary void, a constant physical connection between the Sun and every world that orbits it. The Sun, however, may be an exception in its solitude. While it is the sole star of our solar system, this is not the most common arrangement in the galaxy. More than half of all the Sun-like stars in the Milky Way are not single stars, but are part of multiple star systems, gravitationally bound to one or more stellar companions. These can be binary systems, with two stars orbiting a common center of mass, or even more complex systems with 3 or more stars. The existence of such systems has profound implications for the possibility of life on any orbiting planets. A planet in a binary system might have 2 suns in its sky, leading to complex and extreme variations in daylight and temperature. Orbits in such systems can be unstable, making it difficult for a planet to maintain a steady climate for the long periods necessary for life to evolve. Our single, stable sun may be one of the key factors that makes Earth such a hospitable world. Yet, even in our own relatively stable solar system, we find evidence of past planetary-scale violence. The largest volcano we know of is not on Earth, a planet renowned for its active geology, but on the seemingly quiet and dormant world of Mars. Olympus Mons, which we have visited before, stands as a monument to a time when Mars was a far more active world. Its colossal size, 3 times the height of Mount Everest, speaks to a geological history profoundly different from our own. Its existence reinforces the idea that the processes that shape worlds operate on vastly different scales and over different timelines throughout the cosmos, leaving behind features that challenge our Earth-centric perspectives. While Martian volcanoes have long since fallen silent, the giant storms of the outer planets continue to rage with an intensity and longevity that is difficult to comprehend. The most famous of these is the Great Red Spot on Jupiter, a gigantic anticyclonic storm, essentially high-pressure system that has been churning in the planet's southern hemisphere for centuries. It is an oval-shaped vortex, rotating counterclockwise, and it is so large that the entire Earth could fit comfortably inside it. The storm's distinctive reddish hue remains a mystery, with theories suggesting it could be caused by complex organic molecules or compounds of sulfur and phosphorus being dredged up from deeper within Jupiter's atmosphere and reacting with sunlight. The Great Red Spot is not a permanent feature. It has been observed to be shrinking over the last century, and its ultimate fate is unknown. For now, however, it remains the largest and longest-lived storm known in the solar system, a weather event on a truly planetary scale. Further out, between the orbits of Mars and Jupiter, lies another of the solar system's great features, the asteroid belt. Popular culture often depicts this region as a dense, chaotic field of tumbling rocks, a navigational nightmare for any spacecraft attempting to cross it. The reality, however, is far less dramatic. The asteroid belt is, in fact, an incredibly empty place. The total volume of space it occupies is enormous, and the asteroids within it are spread out over vast distances. While there are millions of asteroids in the belt, the average distance between them is well over 1.5 million kilometers, or about 1 million miles, roughly 4 times the distance between the Earth and the Moon. This means that if you were standing on an asteroid in the belt, you would be extremely unlikely to see another one with the naked eye. Spacecraft flying through the asteroid belt have a vanishingly small chance of a random collision. Every mission to the outer planets, from the Pioneers and Voyagers to Galileo and New Horizons, has passed through the belt without incident. The cinematic image of a high-speed chase through a dense field of cosmic boulders is pure science fiction. The substance of this vast, empty region is also surprisingly slight. If you were to gather up every single asteroid in the main belt, from the largest, the dwarf planet Ceres, down to the smallest pebble, and combine them into a single object, their total mass would be surprisingly small. The combined mass of the entire asteroid belt is estimated to be only about 4% of the mass of Earth's moon. This lack of mass is a crucial clue to the belt's origin. It is not the remains of a single exploded planet, as was once thought. Instead, the asteroid belt is a collection of planetary leftovers, material from the primordial solar nebula that was never able to coalesce into a full-fledged planet. The powerful gravitational influence of nearby Jupiter continuously stirred this material, preventing it from clumping together, and instead keeping it in a state of arrested development. A failed planet, whose scattered remnants continue to orbit the Sun to this day. Our understanding of these celestial features has been built over centuries of human endeavor, a story marked by pioneering individuals who broke new ground. The first woman to travel into the hostile environment of space was Valentina Tereshkova, a Soviet cosmonaut who flew aboard the Vostok 6 mission in 1963. Selected from more than 400 applicants, Tereshkova spent almost 3 days in space, orbiting the Earth 48 times. Her mission was a major propaganda victory for the Soviet Union in the midst of the space race, demonstrating that women were just as capable as men in the demanding field of space exploration. It would be another 2 decades before the first American woman, Sally Ride, would follow her into orbit. Similarly, breaking barriers of race, the first African American in space was Guion S. Bluford, who flew as a mission specialist aboard the Space Shuttle Challenger in 1983. A highly decorated Air Force pilot with a PhD in aerospace engineering, Bluford was a member of the first class of Space Shuttle astronauts, selected in 1978. His historic flight was a landmark moment, opening the door for greater diversity and inclusion in the astronaut corps and in the broader scientific community. These pioneers, and all the astronauts who have followed them, have explored a tiny fraction of the vast cosmic ocean. The portion of the universe that we can, even in principle, observe from Earth is known as the observable universe. This is a spherical region of space centered on us, whose boundary is defined by the distance light has been able to travel since the Big Bang. Because the universe is approximately 13.8 billion years old, we can only see objects whose light has had that long to reach us. However, because the universe has been continuously expanding during that time, the edge of the observable universe is now much farther away than 13.8 billion light years. The current estimate for the diameter of the observable universe is a staggering 93 billion light years. It is a volume so immense that it contains at least several 100 billion, and perhaps as many as 2 trillion galaxies, each containing billions or trillions of stars. And yet, this almost incomprehensibly vast region may itself be only an infinitesimal fraction of the entire universe, which could be infinitely large. We are like sailors on a small raft in the middle of an infinite ocean, able to see only to our own horizon. That horizon of observability, the 93 billion light-year sphere that constitutes our known cosmos, is defined by a fundamental number: the age of the universe itself. Current cosmological models, based on precise measurements of the cosmic microwave background radiation and the rate of universal expansion, place this age at approximately 13.8 billion years. This is the great cosmic calendar against which all events are measured, the time that has elapsed since the Big Bang, the moment when space, time, and all the matter and energy in the universe came into being. This immense span of time is almost impossible for the human mind to grasp. If you were to compress the entire history of the universe into a single calendar year, with the Big Bang occurring at the first second of January 1st, then the first stars would not ignite until mid-January. Our own Milky Way galaxy would form in early March. Our solar system and the Earth would not appear until early September. The first complex life forms would emerge in the oceans in November. The dinosaurs would roam the Earth for a few days in late December, from Christmas Day until the 29th. All of recorded human history, from the ancient Egyptians to the present day, would occupy only the last 10 seconds before midnight on December 31st. Our entire existence is but a fleeting moment in the grand sweep of cosmic time. Within this vast timeline, the birth of the very first stars was a pivotal event, the moment the universe first became illuminated. This cosmic dawn is believed to have occurred approximately 200 million years after the Big Bang. Before this, the universe was in a period known as the Cosmic Dark Ages. It was filled with a uniform fog of neutral hydrogen and helium gas, devoid of any sources of light. But within this smooth, dark fog, tiny quantum fluctuations in density, remnants from the Big Bang itself, were being amplified by gravity. Over millions of years, gravity slowly and patiently drew the densest regions of gas together, pulling them into ever larger and more compact clouds. Eventually, the pressure and temperature at the core of the densest of these clouds became so intense that nuclear fusion ignited. In that instant, the first stars were born, blazing into existence and flooding the dark universe with light for the very first time. These first-generation stars, known as Population 3 stars, were unlike any that exist today. They were forged from the pure, primordial hydrogen and helium of the early universe, and were consequently enormous, hundreds of times more massive than our Sun. They burned through their fuel with incredible ferocity and died in spectacular supernova explosions after only a few million years, seeding the cosmos with the first heavy elements that would be necessary for the formation of planets and eventually life. Not all material in the early universe, however, was successfully corralled into forming stars. Some planets may have been formed in the traditional way, within the protoplanetary disks of young stars, only to be later ejected from their home systems through gravitational interactions with other larger planets. The result is the existence of what are known as rogue planets, or interstellar planets. These are worlds that are not gravitationally bound to any star, but instead wander alone through the cold, dark emptiness of interstellar space. Their existence was long theorized, but has only been confirmed in recent years through a technique called gravitational microlensing. A rogue planet, though dark, has a gravitational field that can bend and magnify the light of a distant background star as it passes in front of it, creating a brief, detectable brightening. Current estimates suggest there could be billions, or even trillions, of these orphan worlds drifting through the Milky Way, outnumbering the stars themselves. These planets would be incredibly cold, their surfaces frozen solid, but it is conceivable that larger, gas giant-sized rogue planets could retain thick hydrogen atmospheres, or that planets with subsurface oceans, like Jupiter's moon Europa, could maintain liquid water through geothermal heat, raising the faint but tantalizing possibility of life in the eternal night. The universe these rogue planets wander through is, on average, an incredibly cold place. If you could somehow place a thermometer in the depths of intergalactic space, far from any star or galaxy, it would register a temperature of approximately 2.7 Kelvin. This is minus 270.45 degrees Celsius, or minus 454.81 degrees Fahrenheit, just a few degrees above absolute zero, the theoretical point at which all atomic motion ceases. This pervasive background temperature is not a measure of the temperature of space itself, which is a vacuum, but is the temperature of the cosmic microwave background radiation that fills it. It is the faint residual heat of the Big Bang, a thermal floor below which nothing in the universe can naturally cool. Every object in the cosmos is constantly bathed in this ancient, feeble warmth, a ubiquitous echo of the universe's fiery birth. Within our own, much warmer solar system, the diversity of celestial bodies is immense, particularly when one considers the vast retinue of moons. While Earth has only one natural satellite, the gas giants of the outer solar system command vast and complex systems of them. As of recent counts, there are more than 200 confirmed moons orbiting the planets in our solar system. Jupiter leads the pack with over 80, including the 4 large Galilean moons, each a world in its own right, and a host of smaller captured asteroids. Saturn, also has over 80, from the giant, hazy Titan to the tiny, ice-spewing Enceladus. Even the dwarf planets in the Kuiper Belt, like Pluto and Eris, are known to have their own moons. Each of these satellites is a unique world with its own history and characteristics, a testament to the incredible variety and complexity that can arise from the processes of planetary formation. The human beings who have ventured into this complex and challenging environment are known by a name that speaks to the poetic soul of exploration. The word astronaut is a modern invention, but its roots are ancient and deep. It is derived from two Greek words, astron, meaning star, and nautis, meaning sailor. An astronaut is, therefore, quite literally, a star sailor. The term beautifully captures the spirit of voyaging into the unknown, of navigating the vast, dark ocean of space. The Soviet, and now Russian, equivalent is cosmonaut, from the Greek kosmos, meaning universe, and notes, giving us universe sailor. Both terms evoke the image of brave explorers setting sail for new and distant shores, a modern continuation of the great voyages of discovery that have defined human history. The very first of these celestial sailors, however, was not human. The first living creature to be sent into orbit was a dog named Laika. She was a stray mongrel from the streets of Moscow, chosen for the Soviet Sputnik 2 mission in 1957, just 1 month after the successful launch of the first satellite, Sputnik 1. Laika was chosen for her calm demeanor and her resilience, qualities that the Soviet space program believed would help her endure the rigors of spaceflight. She was launched into space in a small, pressurized capsule equipped with sensors to monitor her vital signs. The mission was a one-way trip. At the time, the technology for a re-entry and safe landing had not yet been developed. Laika died in orbit a few hours after launch, from overheating when the capsule's thermal control system malfunctioned. Her mission was a landmark moment, proving that a living organism could survive the launch and the environment of weightlessness, paving the way for human spaceflight. Her sacrifice was a tragic but essential step in humanity's journey to the stars. Since that time, our robotic emissaries have traveled much farther. The most distant human-made object is the Voyager 1 spacecraft. Launched in 1977, its primary mission was to study Jupiter and Saturn. After completing its planetary flybys, it continued its journey outward toward the edge of the solar system. In 2012, Voyager 1 crossed the heliopause, the boundary where the sun's solar wind is turned back by the pressure of interstellar gas, and it entered interstellar space. It is now traveling through the vast, empty region between the stars, carrying with it a golden record, a time capsule of sounds and images from Earth, intended as a message for any extraterrestrial civilization that might one day encounter it. Voyager 1 continues to transmit data back to Earth, its faint signals taking more than 22 hours to reach us, a lonely and intrepid explorer in the great cosmic darkness. To peer even deeper into that darkness, we have recently deployed the most powerful space telescope ever built. The James Webb Space Telescope, launched on Christmas Day in 2021, is the scientific successor to the Hubble Space Telescope. Its primary mirror is a massive 6.5 meters, or 21 feet, in diameter, composed of 18 hexagonal, gold-coated beryllium segments. Unlike Hubble, which observes primarily invisible and ultraviolet light, the James Webb Telescope is optimized for infrared astronomy. This allows it to see through the clouds of dust that obscure the birth of stars and planetary systems, and to detect the faint, red-shifted light from the very first galaxies that formed in the early universe. It is a technological marvel, an infrared eye that is allowing us to see the cosmos in a completely new light, pushing the boundaries of our knowledge back to the very dawn of time. The journey that culminated in these incredible machines began with a single, momentous step. The first human being to walk on the surface of another world was Neil Armstrong, the commander of the Apollo 11 mission. On July 20th, 1969, Armstrong descended the ladder of the lunar module Eagle and stepped onto the dusty surface of the moon's Sea of Tranquility. As he took his first step, he uttered the immortal words, "That's one small step for a man, one giant leap for mankind." It was a moment that captivated the entire world, a singular achievement that represented the culmination of a decade of intense effort and the fulfillment of a dream as old as humanity itself. For the first time, a member of our species had left our home planet and set foot on another celestial body, transforming our relationship with the cosmos forever. That giant leap took us to a barren, airless world. But it opened our eyes to the scale and grandeur of the galactic neighborhood we inhabit. Our own Milky Way, a sprawling city of stars, is itself dwarfed by its nearest major rival, the Andromeda Galaxy. We have already encountered Andromeda as our future cosmic dance partner, but its sheer size is worth considering in its own right. The visible disk of the Andromeda Galaxy stretches approximately 220,000 light-years across. This is more than twice the estimated 100,000 light-year diameter of our own Milky Way. If we could see Andromeda in the night sky with its full extent and brightness, it would appear more than 6 times wider than the full moon. It is the true giant of our local group of galaxies, a collection of more than 50 galaxies to which both the Milky Way and Andromeda belong. Its immense size hints at a history of cosmic consumption, a past filled with the mergers of smaller galaxies that have been cannibalized to build its colossal structure, a process our own galaxy is destined to join in the distant future. The study of such cosmic behemoths and the strange phenomena they contain is peppered with terminology that often seems as enigmatic as the objects themselves. The term black hole, now a staple of science fiction and popular science, was not coined until relatively recently in the history of physics. The concept of an object with gravity so strong that not even light could escape dates back to the late 18th century, with the work of the English natural philosopher John Michell. However, for most of the intervening period, these theoretical objects were referred to by more cumbersome names like gravitationally completely collapsed objects or frozen stars. The concise and evocative term black hole was coined in 1967 by the American theoretical physicist John Archibald Wheeler. During a lecture, when struggling for a better term, a member of the audience reportedly shouted out, "How about black hole?" Wheeler immediately adopted it for its descriptive power and simplicity, and it quickly entered the scientific and public lexicon. A perfect name for one of the universe's most profound mysteries. Wheeler's term describes the final fate of the most massive stars, but the death of a slightly less massive star is no less spectacular. This explosive end is known as a supernova, a celestial event of incredible power and transient beauty. A supernova occurs when a star several times more massive than our Sun exhausts the nuclear fuel in its core. With the outward push of fusion energy no longer able to counteract the inward pull of gravity, the star's core collapses catastrophically. This collapse triggers a violent rebound explosion that blasts the star's outer layers into space at speeds of up to 30,000 kilometers per second, or about 67 million miles per hour, roughly 1/10 the speed of light. For a brief period, a single supernova can outshine its entire host galaxy, releasing as much energy as the Sun will in its entire 10 billion year lifetime. This explosion enriches the interstellar medium with heavy elements forged in the star's core and during the explosion itself, providing the raw materials for new generations of stars and planets. Supernovae are the great cosmic recyclers, the violent engines of galactic creation and renewal. The light from our own, much calmer, star takes a more leisurely, though still incredibly swift, journey to reach us. The Earth orbits the Sun at an average distance of about 150 million kilometers, or 93 million miles. Light, traveling at its constant, finite speed, takes time to cross this immense gulf. The light from the Sun that warms your face on a sunny day is not instantaneous. It is, in fact, old news. It takes an average of 8 minutes and 20 seconds for a photon of light to travel from the photosphere of the Sun to the surface of the Earth. This means that if the Sun were to suddenly and inexplicably vanish, we would remain in blissful ignorance for over 8 minutes, continuing to see it in the sky and feel its warmth. Only after that time, delay, would the sky abruptly go dark and the last rays of sunlight finish their journey, plunging our world into an eternal night. While a day on Earth is governed by this steady, predictable source of light. The length of a day on other planets can vary wildly. On the gas giant Jupiter, a day is remarkably short. Despite being the largest planet in the solar system, with a diameter more than 11 times that of Earth, Jupiter is also the fastest spinning. It completes a full rotation on its axis in just under 10 hours. This rapid rotation creates powerful centrifugal forces that cause the planet to bulge significantly at its equator, making it noticeably oblate. It also drives the planet's extreme weather, stretching its clouds into the distinct bands and zones we observe, and powering immense storms like the Great Red Spot. An observer on a floating platform in Jupiter's atmosphere would see the sky whipping by at a dizzying pace, a constant and rapid procession of its many moons against a backdrop of swirling, colorful clouds. The extreme physics that govern such worlds leads to some of the most fascinating theoretical concepts in cosmology. For every well-established phenomenon, like a black hole, there is often a theoretical opposite. The mathematical counterpart to a black hole is a white hole. According to the equations of general relativity, while a black hole is a region of space-time from which nothing, not even light, can escape. A white hole is a hypothetical region from which nothing can enter. It would be a place where matter and light spontaneously erupt outwards, but which could never be reached from the outside. A white hole would essentially be a time-reversed black hole. While there is no known physical process in the universe that could form a white hole, and none have ever been observed, they remain a valid mathematical solution to Einstein's field equations. Some physicists have speculated that they could be connected to black holes via wormholes, or that the Big Bang itself might have been a type of white hole event, a spontaneous eruption of all the matter and energy in the universe from a single point. For now, however, they remain firmly in the realm of intriguing but unproven speculation. Jupiter's immense size and rapid rotation give it another extreme feature: the most powerful magnetic field of any planet in the solar system. This magnetic field is generated deep within the planet's interior by the motion of a vast ocean of liquid metallic hydrogen. The resulting magnetosphere, the region of space dominated by the planet's magnetic field, is a colossal structure. It is so large that if it were visible to the naked eye from Earth, it would appear larger in the night sky than the full moon. This magnetosphere traps charged particles from the solar wind, creating intense radiation belts that are millions of times stronger than Earth's Van Allen belts, posing a significant hazard to any spacecraft that venture too close. It also interacts with Jupiter's moons, creating powerful electrical currents and auroras that are far more spectacular than our own northern and southern lights. The color of the stars that illuminate these distant planetary systems is not merely an aesthetic detail. It is a direct indicator of their surface temperature. Just like a piece of iron heated in a blacksmith's forge, stars glow with different colors depending on how hot they are. The coolest stars, with surface temperatures around 2,500 to 3,500 degrees Celsius, or 4,500 to 6,300 degrees Fahrenheit, appear red. Our Sun, a medium-temperature star at about 5,500 degrees Celsius, or 9,900 degrees Fahrenheit, appears yellow-white. The hottest stars, however, with scorching surface temperatures exceeding 25,000 degrees Celsius, or 45,000 degrees Fahrenheit, blaze with a brilliant blue-white light. So when you look up at the night sky and see the reddish tint of Betelgeuse or the brilliant blue of Rigel in the constellation Orion, you are seeing a direct visual representation of their stellar thermometers. This cosmic thermometer has allowed for a remarkable coincidence to occur in our own sky. The phenomenon of a total solar eclipse, where the moon perfectly blocks the face of the sun, is a product of a stunning celestial alignment that is unique to our time and place in the universe. The sun is approximately 400 times larger in diameter than the moon. By a sheer improbable coincidence, the sun is also approximately 400 times farther away from the Earth than the moon is. This precise ratio of size and distance makes the two objects appear to be almost exactly the same size in our sky. This allows the moon, during a total solar eclipse, to perfectly cover the sun's bright photosphere, revealing the faint, ethereal outer atmosphere, the corona, which is normally invisible. This perfect alignment is not permanent. As we know, the moon is slowly drifting away from the Earth. In the distant past, it was closer and appeared larger, completely blocking the corona. In the far future, it will be more distant and will appear smaller, unable to completely cover the sun, making total solar. Eclipses a thing of the past. We live in the brief, fortunate window of cosmic time when this beautiful celestial happenstance is possible. The equipment required to venture into this celestial environment, to sail among the stars, is a marvel of engineering. The process of an astronaut putting on their spacesuit, a procedure known as a suit-up, is a complex and time-consuming ritual. It can take up to 45 minutes for an astronaut to don their multi-layered personal spacecraft. This includes putting on a cooling garment that circulates water to regulate body temperature, followed by the main torso, helmet, and gloves of the suit itself. After assembly, the astronaut must spend a significant amount of time pre-breathing pure oxygen to purge the nitrogen from their bloodstream. This is necessary to prevent decompression sickness, or the bends, when they transition to the low-pressure, pure oxygen environment of the suit. It is a meticulous and deliberate process, a testament to the extreme care required to survive in the vacuum of space. This meticulous preparation allows humans to exist, however briefly, in a cosmos whose scale can be almost paralyzing to contemplate. We organize the universe into galaxies and clusters of galaxies, but even these structures are dwarfed by larger, more tenuous formations. Among the largest known structures in the entire observable universe is a colossal filament of galaxies known as the Great Wall of Sloan. Discovered in 2003 through the Sloan Digital Sky Survey, a major project to map the positions of millions of galaxies, this wall is a vast, elongated supercluster of galaxies, a cosmic web of galactic groups connected by gravitational tendrils. It stretches for an astonishing 1.37 billion light-years. To put this distance into perspective, if the entire Milky Way galaxy were the size of a dinner plate, the Great Wall of Sloan would be a structure more than 2 kilometers, or well over a mile, long. It is not a solid object, but a region of space where the density of galaxies is significantly higher than the cosmic average. Its existence challenges our models of how the universe evolved, as the time required for gravity to assemble such a gargantuan structure is close to the age of the universe itself. It is a stark reminder that on the largest scales, the cosmos is not uniform, but is organized into a magnificent web-like pattern of walls, filaments, and vast, empty voids. The tempo of life and time within these cosmic structures varies dramatically from world to world. We return to the blistering inner realm of the solar system, to Mercury, the swiftest of all the planets. Its proximity to the Sun gives it the shortest year of any planet, a rapid journey of just 88 Earth days. In the time it takes for Earth to complete one full season, Mercury has already completed an entire trip around the Sun. An inhabitant of Mercury would celebrate their birthday 4 times for every single year that passes on Earth. This fleeting year, combined with its incredibly long 176-day solar day, creates a bizarre temporal landscape where a single day lasts for 2 full years. It is a world of extreme temporal contrasts, a place where time itself seems to behave in an alien and counterintuitive way. The gravitational forces that dictate these orbital periods also govern the physical experience of being on a particular world. The force of gravity on the surface of a celestial body depends on its mass and its radius. Our moon, being significantly less massive and smaller than the Earth, has a much weaker gravitational pull. The surface gravity on the moon is only about 1/6 of that on Earth. This means that a person who weighs 80 kilograms, or about 176 pounds, on Earth would weigh a mere 13 kilograms, or about 29 pounds, on the moon. This is why the Apollo astronauts were able to bound and leap across the lunar surface with such ease, their heavy, cumbersome spacesuits feeling remarkably light in the gentle lunar gravity. This simple fact of physics would be one of the most fundamental and transformative aspects of life on another world, reshaping everything from locomotion to architecture. Our home galaxy, the Milky Way, is the grand stage upon which these phenomena play out. We classify it as a barred spiral galaxy, a beautiful and dynamic structure composed of several main components. At its center is a dense, bar-shaped structure of older, redder stars. Extending from the ends of this central bar are four major spiral arms, vast, curving lanes of gas, dust, and young, bright blue stars. Our own solar system is located in a smaller partial arm or spur known as the Orion Arm or the Orion Cygnus Arm. We are situated about 2/3 of the way out from the galactic center in a relatively quiet and stable region, far from the intense radiation of the core and the chaotic star-forming regions of the major arms. It is, in many ways, a prime piece of galactic real estate, a calm harbor that may have been crucial for the long-term stability needed for complex life to evolve. It is from this harbor that we now look out and find that we are not alone in having a planetary companion. The nearest star to our solar system is a small, dim, red dwarf named Proxima Centauri, part of the Alpha Centauri triple star system. It lies a mere 4.2 light-years away, a stone's throw in cosmic terms, yet still an unbridgeable chasm for our current technology. In 2016, astronomers confirmed the existence of an exoplanet orbiting this closest of stellar neighbors. The planet, named Proxima Centauri b, is a rocky, Earth-sized world. Most excitingly, it orbits within Proxima Centauri's habitable zone, the region where temperatures could allow for the existence of liquid water on its surface. However, its parent star is a volatile red dwarf, prone to violent flares that could blast the planet with intense radiation, potentially stripping away its atmosphere and making the emergence of life difficult. Despite these challenges, Proxima Centauri b remains a tantalizing target, the closest known exoplanet, and a prime candidate for future interstellar probes, a neighboring world that beckons us to explore. While Proxima Centauri b is our closest exoplanetary neighbor, the title of the largest known galaxy in the universe belongs to a true cosmic titan named IC 1101. It is a supergiant elliptical galaxy located nearly 1 billion light-years away at the center of a rich galaxy cluster called Abell 2029. Its sheer scale is mind-boggling. IC 1101 is estimated to be about 50 times the size of the Milky Way and 2,000 times more massive. It has a diameter of somewhere between 4 and 6 million light-years. If it were in the place of our galaxy, it would swallow up not only the Milky Way, but also the Andromeda Galaxy, the Triangulum Galaxy, and most of the other galaxies in our local group. It is thought to have grown to this monstrous size through a long history of galactic cannibalism, merging with countless other smaller galaxies over billions of years. It is a quiet, sedate giant, composed mostly of old, yellow stars, its era of frantic growth now long past, a serene monarch reigning over its galactic cluster. The universe that contains these colossal structures appears, on the largest scales, to be homogeneous and isotropic, meaning it looks the same in every direction. This has led to a profound and humbling realization. The universe has no known center or edge. In the Big Bang model, the expansion of the universe is not like an explosion in pre-existing space, with matter rushing out from a central point. Instead, it is an expansion of space-time itself. Every point in the universe is moving away from every other point. An observer on any galaxy would see all other galaxies, except those gravitationally bound to it, rushing away from them, creating the illusion that they are at the center of the expansion. There is no special vantage point, no privileged location in the cosmos. Similarly, the concept of an edge to the universe is likely meaningless. While our observable universe has an edge, the horizon beyond which light has not had time to reach us, the universe as a whole may be infinite. If it is finite, it is likely to be unbounded, meaning it curves back on itself, like the surface of a sphere. In such a universe, if you were to travel in a straight line for long enough, you would eventually end up back where you started, without ever having reached an edge. Within this boundless universe, the most common type of star is not the bright, sun-like star we are familiar with, but a much smaller, cooler, and dimmer type of star, the red dwarf. These stars are the celestial underachievers of the cosmos. They have a mass of between about 8% and 50% of that of our sun, and they burn their hydrogen fuel incredibly slowly. Their surface temperatures are low, giving them a faint, reddish glow. Because they are so dim, not a single red dwarf is visible to the naked eye from Earth, despite them making up an estimated 75% of all the stars in the Milky Way. Their slow, frugal consumption of fuel gives them extraordinarily long lifespans, potentially trillions of years, far longer than the current age of the universe. When the sun and other larger stars have long since burned out, the red dwarfs will continue to shine feebly in the cosmic twilight, the last lights to go out in a dying universe. The concepts that underpin our understanding of this universe, from black holes to dark matter, are the product of centuries of scientific inquiry. The first person to seriously propose the idea of a black hole, though he did not use the term, was the English natural philosopher John Michell, in a letter written in 1783. A brilliant and wide-ranging thinker, Michell reasoned that if light was a particle, as Isaac Newton had proposed, then it should be affected by gravity. He calculated that a star 500 times the diameter of the sun, but with the same density, would have a surface gravity so strong that its escape velocity would be greater than the speed of light. Any light emitted from the surface of such a star would be pulled back by its gravity, rendering it invisible to a distant observer. Michell called these hypothetical objects dark stars. His idea was too far ahead of its time and was largely ignored for over a century. But it stands as a remarkable piece of early theoretical insight into the nature of gravity and light. Similarly, the concept of dark matter, the invisible substance that now dominates our model of the cosmos, has its roots in the early 20th century. In the 1930s, the Swiss-American astronomer Fritz Zwicky was studying the Coma cluster of galaxies. He observed that the individual galaxies within the cluster were moving far too quickly. According to his calculations, the total visible mass of all the stars in the cluster was not nearly enough to generate the gravitational pull needed to hold the rapidly moving galaxies together. The cluster should have flown apart long ago. To account for this discrepancy, Zwicky proposed the existence of a huge amount of unseen matter, which he called dunkel materia, or dark matter. Like Michel's dark stars, Zwicky's idea was largely dismissed by the scientific community for decades. It was not until the 1970s, when astronomers like Vera Rubin found similar evidence in the rotation of individual galaxies, that the concept of dark matter was finally taken seriously, becoming a cornerstone of modern cosmology. Zwicky's revolutionary idea, born from observing the frantic dance of distant galaxies, remained a theoretical necessity for over 80 years. Dark matter was a ghost in the cosmic machine, its presence inferred, but never directly seen. This changed, in a way, for its even more mysterious cousin, the black hole. While John Michel had conceived of a dark star in the 18th century, and John Wheeler had given it a name in the 20th, the ultimate proof, a direct image, remained elusive. This was a challenge of almost unimaginable difficulty. A black hole, by its very nature, emits no light. Furthermore, even the supermassive black hole at the center of our own galaxy, Sagittarius A star, is a tiny speck on the sky, its apparent size equivalent to trying to see a donut sitting on the surface of the moon. No single telescope on Earth could ever hope to resolve such a small object. The solution was as audacious as it was brilliant: to create a telescope the size of the Earth itself. This was the goal of the Event Horizon Telescope project, a global collaboration that synchronized a network of radio telescopes scattered across the planet, from the mountains of Chile to the South Pole. Using a technique called very long baseline interferometry, they were able to combine the data from all these individual dishes, effectively creating a single planet-sized virtual telescope. After years of observations and painstaking data processing, in April of 2019, the team unveiled the first ever direct image of a black hole and its event horizon. The image was of the supermassive black hole at the heart of the galaxy, Messier 87, a behemoth 6.5 billion times the mass of our Sun. The picture showed a dark central shadow, the point of no return, silhouetted against a lopsided, glowing ring of superheated gas, the accretion disk that was being whipped around it at near the speed of light. It was a momentous achievement, a visual confirmation of one of Einstein's most profound predictions, and a testament to the power of human ingenuity and collaboration. The galaxy that this black hole anchors, like our own, bears a name rooted in ancient observation. The very word galaxy is a tribute to how our own stellar home appears from our vantage point within it. It comes from the Greek word galaxias, which in turn is derived from gala, the Greek word for milk. To the ancient Greeks, the faint, hazy band of light that stretches across the night sky looked like a milky circle, a celestial river of light. We now know this milky band is the combined light of billions of distant, unresolved stars in the disk of our own galaxy, viewed from the inside. This poetic, ancient name, the Milky Way, is a constant and beautiful reminder of our long and evolving relationship with the night sky, a journey from mythological interpretation to scientific understanding. Within this milky river of stars, certain patterns have captivated human imagination for millennia. Among the most recognizable of these is the constellation of Orion, the Hunter. This prominent grouping of bright stars is a fixture of the winter sky in the northern hemisphere and the summer sky in the southern hemisphere, making it one of the few constellations that is visible from almost anywhere on Earth. Its distinctive belt of 3 bright stars in a straight line, Al-Nitak, Al-Nilam, and Mintaka, makes it easy to identify. The constellation is rich with celestial wonders, including the brilliant red supergiant Betelgeuse, the hot blue supergiant Rigel, and the magnificent Orion Nebula, a vast stellar nursery where new stars are being born, visible to the naked eye as a fuzzy patch in Orion's sword. Its universal visibility has made it a cornerstone of mythology and navigation for countless cultures throughout human history. The stars that form these familiar patterns, like Betelgeuse and Rigel, exist in a state of delicate balance, a constant battle between gravity and the outward pressure of nuclear fusion. At the heart of a star like our Sun, the conditions are truly extreme. The hottest part of the Sun is its core, where temperatures reach a staggering 15 million degrees Celsius, or about 27 million degrees Fahrenheit. It is here, under the immense pressure created by the star's own gravity, that hydrogen atoms are fused together to form helium, releasing the vast amounts of energy that make the Sun shine. This energy then travels outward through the star's interior over hundreds of thousands of years. Paradoxically, the coolest part of the Sun that we can observe is its visible surface, the photosphere. Here, the temperature has dropped to a relatively mild 5,500 degrees Celsius, or about 9,900 degrees Fahrenheit. It is from this cool surface that the sunlight we see finally escapes into space, embarking on its 8-minute journey to Earth. The number of such suns in the universe is a figure that continues to grow as our observational capabilities improve. For a long time, estimates based on deep field images from the Hubble Space Telescope placed the number of galaxies in the observable universe at around 1 to 200 billion. However, more recent and sophisticated analyses, incorporating data from other surveys and improved models of galaxy formation, have suggested that this number was a significant underestimate. Many distant, fainter galaxies were simply beyond Hubble's ability to detect. The current consensus is that there are likely up to 2 trillion galaxies in the observable universe. This means that for every single star in our own Milky Way galaxy, there is another entire galaxy somewhere out there in the cosmic darkness. It is a number so large that it redefines our sense of place, transforming our vast home galaxy into just one of countless grains of sand on an infinite cosmic shore. The scientific discipline that grapples with these immense numbers and the profound questions they raise is cosmology, the study of the origin, evolution, and ultimate fate of the universe. Cosmology operates on the largest possible scales of space and time. It seeks to answer the most fundamental questions of existence. Where did everything come from? What is it made of? And where is it all going? It is a field that blends observational astronomy with theoretical physics, using data from powerful telescopes to test and refine theories that stretch the very limits of our understanding. From the quantum weirdness of the Big Bang to the enigmatic nature of dark energy. While cosmologists study the grandest of scales, astronauts experience the cosmos on a very human scale, and it has a measurable physical effect on their bodies. One of the most curious of these effects is that astronauts can actually grow taller in space. On Earth, the constant force of gravity compresses our spines. The gelatinous, fluid-filled discs between our vertebrae are slightly squeezed. In the microgravity environment of space, this compressive force is removed. The spinal discs are able to expand, and the spine lengthens. As a result, an astronaut can grow by up to 3% of their height, which can mean an increase of up to 2 inches, or about 5 centimeters, for an average adult. This height increase is temporary. Upon returning to Earth's gravity, the spine is recompressed, and the astronaut returns to their normal height within a few months. It is a striking, personal demonstration of the pervasive and constant influence of gravity on our bodies. Our ability to perceive and study these cosmic phenomena began with a revolutionary invention. The first telescope was invented not by a scientist, but likely by a Dutch spectacle maker named Hans Lippershey in 1608. He discovered that by placing 2 lenses in a tube, he could make distant objects appear closer. The initial applications were military and commercial, for spotting ships at sea. However, it was the Italian astronomer Galileo Galilei who in 1609 first turned this new invention towards the heavens. His small, crude telescope revealed wonders that shattered the ancient, Earth-centered model of the universe. He saw mountains and craters on the moon, discovered the 4 largest moons of Jupiter orbiting the giant planet, and observed the phases of Venus, providing crucial evidence that the planets orbited the Sun. The telescope was more than just an instrument. It was a new set of eyes for humanity, opening a window to the cosmos that we are still looking through today. To measure the immense distances revealed by this window, we needed a new unit of measurement. A light year is a measure of distance, not time, a distinction that often causes confusion. It is defined as the distance that light travels in a vacuum in 1 Julian year. Given that light travels at nearly 300,000 kilometers per second, this distance is enormous. A light year is approximately 9.46 trillion kilometers, or about 5.88 trillion miles. This unit allows astronomers to discuss the vast distances to stars and galaxies in a more manageable way. Saying that Proxima Centauri is 4.2 light-years away is far more convenient than saying it is nearly 40 trillion kilometers away. The use of the light year also elegantly combines distance and time, reminding us that as we look farther out into space, we are also looking further back into the past. Our journey into that past, our entire space age, began with a single beeping sphere. The first artificial satellite to be placed in orbit around the Earth was Sputnik 1, launched by the Soviet Union on October 4th, 1957. It was a simple, polished metal sphere, just 58 centimeters, or 23 inches, in diameter, with 4 long antennas. It carried no scientific instruments, only a radio transmitter that broadcast a steady, rhythmic beep that could be heard by radio operators all over the world. That simple, repetitive signal was a profound announcement to the world. It marked the dawn of the space age, demonstrating that humanity now possessed the technology to break the bonds of Earth's gravity and place objects in orbit. The launch of Sputnik was a stunning scientific and political achievement that ignited the space race, a period of intense competition between the United States and the Soviet Union that would ultimately lead to the Apollo moon landings and the incredible era of space exploration that continues to this day. And so, our journey through the cosmos returns to where it began, here on the quiet surface of our world, looking up. From the familiar scent of raspberries in the heart of our galaxy to the silent fall of diamond rain on worlds impossibly far, we have traversed a universe that is at once alien and intimately connected to us. We have learned that the gold in our hands was forged in the collision of dead stars, and that our planet is constantly dusted with the remnants of ancient comets and asteroids. We have seen that the steady light of the stars is an illusion of our atmosphere, and that the beautiful, total eclipse of our sun is a fleeting, cosmic coincidence. The darkness between the stars is no longer empty, but filled with the quiet hum of creation. With rogue worlds and dying suns, with the echoes of a beginning we can still faintly hear. The universe, for all its silent, sprawling grandeur, has in us found a voice, a consciousness capable of looking back upon it and marveling at its own origins. The story of the cosmos is not just a story of distant objects and abstract forces. It is our own story, written on the grandest possible scale. It is a story that invites us, always, to simply look up and to wonder.